Hi, linear algebra students. This is arguably the most important theorem in the theory of invertible matrices, and we're going to prove it. So if A is a n by n matrix, it is invertible if and only if A is row equivalent to I. Okay, so we're going to prove, basically the idea is to prove both directions. Okay, so we begin with this direction. So this will be, I will call this step number 1. So we will prove this direction, which is actually fairly obvious when you think about it. So the most important aspect of the theorem is actually the reverse way. But that being said, let's actually see why this is true. So if A is invertible, then AX equals B has unique solution X equals A minus 1B. So what does it mean? It means first that the system is always consistent. So since AX equals B is always consistent, A has a pivot in every row. However, we also know that the solution is unique. So by uniqueness of the solution, A has a pivot in every column. Okay, so what do we know about its RREF? Okay, so what does it mean? So it's RREF. Okay, so first of all the non-pivot elements happen to be 0, and this is because you have a pivot in every column. So everything above or below needs to be 0. So every non-pivot in the RREF are zeros. Okay, so this is because each column is a pivot column. So we don't have any like non-pivot column in which we could have something that is not a pivot, but that's also not 0. Okay, what else do we know? Well, we know that the pivots are going to lie on the diagonal elements. And this is because this is the, okay, so since each leading entry is at the left of leading entries of rows below, they happen to be on the diagonal element. And that's really because you have one on each row and one on each column. They are on diagonal. Okay, so, and this is because since pivot in each row and in each column. Okay, so what does it mean? Well, quite simple. every non-pivot is 0. Each leading entry are on the diagonal. Okay, and they are ones. So again in our REF, so each pivot is 1. Okay, and this means that the RREF of A is actually the identity matrix of A is IN. Now keep in mind, this is the end of the proof for that part. Okay, so this I will say here QED for the arrow like this. So we prove that A is invertible only if A is row equivalent to IN. Now let's prove the other way around. So step number 2. And I need to erase everything, so take note. So we need to prove that A is invertible if A is row equivalent to I. So now we go the other way around. We suppose that A is row equivalent to I. So if A is row equivalent to IN, now we're going to use elementary matrices. These are what they are for. So there are elementary matrices. So we call them like E1, E2, all the way up to EK minus 1, EK, okay, for which if you apply them in the reverse order on A, so EK, EK minus 1, all the way down to E2, E1, A, you get the identity matrix. Okay, then, so since each elementary matrix is invertible, Terry matrix is invertible, we have that the matrix EK all the way down to E1 is invertible. So what it means is that we can multiply both sides of this equation by the inverse. So multiply both sides by the inverse. Okay. So what will happen then? Inverse here. Then what it means is that we will have like this. So EK down to E1 inverse times like EK, EK minus 1, E2, E1, A, okay, is equal to, so EK, that's it, E1 inverse, times the matrix I, okay? And I'm going to go slightly faster because you can do this like by associativity. You can actually say that this is going to translate into A being equal to just this thing. So EK inverse. So what did we discover? Well, we discovered that A is the inverse of a matrix. So since since A is the inverse of a matrix, it's itself invertible. And this follows from the rule that a negative 1, negative 1 is equal to a. So if you can write if you can write a being a negative 1 to the negative 1, like if you find a matrix for which a is the inverse of, then a automatically is itself invertible. All right, and this is the end of the proof for the reverse direction. So QED for this part. So I hope this helped. See you either in the next video or in class.